Okay, welcome back everyone. It's nice to see you. I hope you had a good weekend. How's everybody doing today? All right. Well, I hope you're doing well and staying as safe as you can be. I know it's a challenge at this time. I'm doing fairly well too, and I appreciate you asking. Thank you, Jennifer. Okay, so do any of you have questions about the lecture exam from last Thursday? Any questions? As I said, the class average on that was about an 82%, which is pretty good. Okay. All right, before we start new material today, I thought I would just take a moment and show you how to calculate your course grades at this time so that you have an idea where you stand in the course as you head in towards the final exam next week, right? We have 2 weeks left, including this week. Not this Thursday, but the following Thursday, you take your final exam and it's all over, folks, okay? So let me show you how you can estimate what your grade is in the course at this time. So I'm gonna share with you a Microsoft Excel document here, a screen, and just go through some basic ideas with you. So bear with me one moment. Okay, so you should see my desktop right now, which is black and white with some buildings. And I'm bringing in Microsoft Excel here. Okay. All right, and I'm going to magnify this a little bit. Okay. So again, what we're doing here is giving you an idea of how to calculate your course grade. Okay, so I'm going to simply list some headings up at the top of the document. You don't have to do it this way, but I think it's easy if you have access to a spreadsheet. It's easy to do these calculations. You can do the same thing with a calculator sitting in front of you. You just have to be organized. Okay. All right. So we're going to list 4 things out. They are the exams in column A, the score of those exams in column B, the weight of those exams in column C, which come from the very first page of your course syllabus, and then the weighted score. Okay, so it's going to look like this, folks. In this course, we have 3 lecture exams. So that's lecture exam 1, lecture exam 2, lecture exam 3. And we have 2 lab exams, lab exam 1, lab exam 2. Okay. Now the weights of each of these exams is listed on your syllabus. If you don't have that, that's okay. I'll list them out for you today. Okay, lecture exam 1 is 26%, has a 26% weight. So to do the calculation, you need to put it in as a decimal percent. So that would be 0.26. The second lecture exam is also 26%, so that's 0.26. The third lecture exam, which is your final exam, is 23%, so that's 0.23. Lab exam 1 was 10%, which is 0.10. Lab exam 2 is 0.15 or 15%. And what you'll notice is if you add all of these weights up, they will calculate up to 1, meaning 100%. Okay, so to calculate your grade in the course, or to give yourself an estimate of how you stand in the course at this time, what you need to do is put your scores of your exams in column B. So I'm not going to put I'm not going to use anyone's grades here. I'm not going to show that to anybody. But obviously, you want to do the calculation with your own personal scores. So for lecture exam 1, let's say, I think the class average was maybe somewhere around the 78%. So I'm going to put 0.78 as a score. For lecture exam 2, the class average was around an 82%, so I'm going to put in 0.82. Okay. For lecture exam 3, we haven't done it yet, so I'm going to color it yellow. For lab exam 1, we have done that, and I believe the class average was around a 90% on that. And lab exam 2, you have not done yet because that is Thursday's exam for you. Okay? So here's the deal, folks. It is impossible to calculate exactly what your course grade is. But what you can do is estimate what you might finish the course with. So to estimate it, what you have to do is put in an estimate of how well you think you can score on lecture exam 3 and how well you think you can score on lab exam 2. So everything that's shaded yellow is going to be an estimate. Okay, you're making an estimate. So for lecture exam 3, let's say, I'm going to say maybe the class average goes to an 85%. And for lab exam 2, I'm going to say that the class average drops to an 87%. Okay, those are just estimates. We're playing a numbers game at this point. So you want to put your personal scores in column B, and for your third lecture exam and your lab exam, you need to make an estimate of what you think you can score. Okay? So once you do that, to get the weighted scores in column D, you take the value in column B and you multiply it by the value in column C. So it's B2 times C2 to give me the weighted score. And I will do the same calculation for everything in column D simply by dragging down with the spreadsheet. The spreadsheet knows that I want to do the same calculation where I take a score in column B and multiply it by a weight in column C. And you do that for everything in column D. Then to get your final grade, what you do is take everything in column D and you add it together. So that would be the sum, right? I'm going to take the sum of all of these weighted scores. Okay? So, in other words, the final grade that we've calculated here obviously is hypothetical because I'm just using some random numbers here. I'm not using anyone's personal scores. Okay? But this final grade is in fact mathematically correct if your assumptions, if your estimates are in fact accurate. Okay? So by doing the calculation this way, you can see where you stand in the course, what direction you're heading for a letter grade, and you can always update the calculation, right? Everything in yellow, you could change it. You could say to yourself, well, what if I get an 80? What if I get an 80 on the third lecture exam? You notice that the calculation immediately updates. What if I get a 90 on the lab exam? The calculation immediately updates. So by doing it this way, you can get a feel for what grade you're likely to finish with, assuming that your estimates are correct. Okay. All right, folks, is this making sense? What's happening here? Do you need me to explain anything again? Okay. All right, not hearing anything. So, folks, just for my own well-being, if you can hear me right now, please type yes into the chat window. Okay, great. All right, so does anyone have any questions about how to do the grade calculation before I take this off the screen? Okay, I think many of you are in pretty good shape, but again, it's worthwhile spending a moment to do this calculation to see where you're trending towards. Okay. Okay, so let's continue, folks. All right, so what we're going to do today is finish chapter 11. And if there's time, we're definitely going to get into chapter 12 as well, okay? Because we are racing towards the end of our semester, right? Thursday, you have your second lab exam. And then a week from Thursday, you have the final exam for the course, which is lecture exam 3. Okay, folks, let's see what we can do here. Okay, so at the end of last class, I believe we had been talking a little bit about stem cells, and I showed you that video about, growing a bioengineered kidney in the lab, and we had a little bit of philosophical conversation about, would we as a society want to do these things, and who's going to pay for it, and will you want to work longer before you have to retire, and all that kind of good stuff, okay? So we're going to get back to some basic information at this time. What I want to do is highlight the cells that you find on page 200 of your textbook, table 11.1. So these will be types of formed elements in the blood, and I'm going to encourage you to have page 200 of your textbook available, table 11.1. Okay. All right. So let's actually start. I'm going to start with the white blood cells. Okay. In some ways, they're kind of the most interesting part of the blood. The white blood cells, as you know, are properly known as leukocytes, right? There's two major categories. There are the granulocytes and the agranulocytes. Okay. Question coming through the chat window. Why are granulocytes, given that why are granulocytes called granulocytes? Why are granulocytes called or given the name granulocytes? Why is that? Any thoughts on that? Okay, Quinn, I like the thinking. It's not correct, but I still appreciate the effort. They are grand, but both categories are actually very important to defend yourself. Okay, anything else? Okay, well, let me, okay. Sometimes they are bigger, Quinn, but not always, okay? So let me draw your attention. If you're looking at page 200, folks, take a look at the granulocytes and compare it to the agranulocytes. How does the cytoplasm of the granulocytes look? Visibly speaking, what does the cytoplasm of the granulocytes look like? What is the appearance of the granulocyte cytoplasm? Okay, Emily, it has small particles in it, right? It looks like glitter, absolutely. It looks kind of dirty, kind of sandy, like there's spots in it. Folks, that's why granulocytes are called granulocytes, because there are these visible granules, like, they're not grains of sand, but they kind of look like grains of sand in the cytoplasm. Okay, and You know, if we had been together in the lab, I could have shown you some things under the microscope that you could have seen this for yourself. Okay, but granulocytes are given this name because of the granular appearance of their cytoplasm. Okay, obviously the agranulocytes do not have this granular, dirty, sandy appearance to them. Okay, so there is something different here. Okay, does anybody have an idea what these granules actually are? What are these granules in the granulocytes? I would be super mega impressed if you can tell me, because I don't think your book tells you. Okay. Okay, Quinn, very good. Lysosomes, very good, very good. That's exactly correct. The granulocytes, the granular material in the cytoplasm, is due to an abundance of a whole bunch of lysosomes, okay? So let's see what we can say here. The granular appearance is due to the presence of many lysosomes, okay? Very nice. And so the agranulocytes, okay, the agranulocytes, they do have lysosomes. They just don't have nearly as many as the granulocytes, okay? So agranulocytes do have lysosomes, but not as many as the granulocytes, which is why these cells do not have a granular appearance. Okay. All right, folks. Let's take a look at the various kinds of granulocytes. Okay. So the types here. All right, so the first type are the neutrophils. Okay, the neutrophils that you can see for yourself. Okay, I like to think of the neutrophils as sort of the Marines of the white blood cells. Okay, if we're thinking of white blood cells as cells that are involved with body defense. Okay, let's put that up there. We're going to be talking that in great detail in chapter 13, but let me just hint at it here in your notes. Okay, as body defense cells. Okay, neutrophils are kind of like the Marines, and what I mean by that is, you know, if there's a trouble spot on the planet, it's frequently true, although not always true, that a lot of times the Marines might see action before the other armed forces, and so that's how I want you to think about the neutrophils. The neutrophils are often present at an infection site before other categories of cells arrive. Okay, these are kind of the Marines in that they arrive at an infection site before other defense cells. Okay. And one thing I would want you to know about them is that neutrophils are very good at phagocytosing bacteria. You recall from other reading you've probably done that phagocytes are any kind of cell that have the ability to engulf and phagocytose material, right? Remember that phagocytosis is a form of endocytosis. We talked about that a little bit in chapter 3. So when we say that the neutrophils are good at phagocytosing bacteria, that kind of means that they're good at eating the bacteria, okay? The end goal, of course, is to destroy the bacteria, and they are frequently successful at doing that. Okay, please ask questions along the way, gang. Otherwise, I'm going to keep rolling to make sure we get everything in your notes here. Okay, so eosinophils is next. Eosinophils. Okay. Eosinophils do a lot of things in the body, but one thing we'll say and put in your notes here is Mother Nature created eosinophils to attack parasitic worms. These are your body's defenders against parasitic worms. Okay. Now you might say to yourself, well, I don't have any parasitic worms. And that's most likely true. We are fortunate to live in a time and in a place where we have access to adequate supplies of clean water and hopefully fairly parasite-free food sources, okay? But please understand that was not always true in terms of our ancestors many generations ago. And it's still often not true in many parts of the underdeveloped world. People are still exposed to parasitic worms every day across the globe. And so Mother Nature, through the hundreds of thousands of years of evolution, had to create a cell that was optimized to attack parasitic worms. Okay. So let me see here. Okay. So as I look at you, if you are able to turn on your video camera, please do so. Okay. Folks, just give me a quick gut reaction to my next question. If you feel a little bit tired today, please raise your hand. Okay, folks, tiredness is one of the primary symptoms of a parasitic worm infection. There you go. Okay, think about that. Okay. All right, I'm joking with you. I'm not joking with you. Tiredness is a primary symptom, but I'm not suggesting that you really have a worm. Okay. All right, very good. Let's continue here. Do you have any questions right now? Okay, here we go. Let's continue. All right. So yes, eosinophils are good at attacking parasitic worms. Okay. The next category are your basophils. Okay, so go ahead and look at these on page 200. Basophils are one of the primary cells of the body that have the ability to release histamine. And let me be sure I bring up my chat window here again for you. Okay, so basophils can release histamine. Folks, question coming through the chat window. What does histamine do to blood vessels? Okay, right. So, okay, Gwen and Nick, right? You're thinking about the right thing, right? Now, histamine is not involved in clotting. No, okay, but you both said something that puts us on the right track, and that's my point. Histamine will widen the blood vessels. Widen is known as dilation. Okay, so basophils are one of the primary cell types that can release histamine. Okay, histamine has the ability to widen, meaning dilate blood vessels, okay? And you can imagine that the whole purpose of widening a blood vessel is because if I widen the blood vessel, that's like taking the road outside your house and making it wider. We can bring more traffic through that space in the same amount of time. If I widen the blood vessels, I can bring more defense cells to potential problem site quicker, okay? This allows more defense cells to travel to a problem site more rapidly. Okay. All right, folks. Do you have any questions right now about the granulocytes? Okay, not seeing anything. I will continue. Let's take a look at the agranulocytes. Okay, there are two major types here. First, we have monocytes. Okay, you know, as with most things about this course, folks, right, we often just tell you one kind of little thing to whet your appetite and give you an idea. Everything we're talking about here does have a variety of other things that they can be involved with. For monocytes, what I'll tell you about those is that monocytes are the precursor cells to macrophages. Okay, monocytes are the precursor cells to macrophages. Okay, and you might recall that macrophages are another type of cell that has phagocytic ability. I see your question, Quinn. Okay, so macrophages are very important at phagocytosing invaders, and they develop from monocytes. Okay, macrophages are also heavily involved in actually activating your adaptive immune system, and that's something we're going to encounter in chapter 13. Okay, so let me just highlight that briefly here. Macrophages are also important to activate the immune system. Okay, so obviously I'm describing a lot of things that macrophages do, but macrophages don't start out as macrophages, they start out as monocytes. So monocytes are the precursor cells to the macrophages. Okay, Quinn, you asked, do these cells benefit from absorbing the parasites or bacteria? That's an interesting idea. I would say that the dogma in the field is that the cells that are ingesting these bacteria are seeking to destroy the microorganism and be done with it. However, it is possible that some of the DNA from the digested bacterial cell could be put into the DNA of the macrophage or neutrophil as a way of retaining a form of cellular memory about the invader. So it may benefit us from that perspective. I'm not saying that it happens all the time, but I think there's some evidence that it happens sometimes. Okay. Other questions? Okay, let's continue. Another category of agranulocyte is going to be the lymphocytes. Okay, be very careful with that, folks, because you know there are words here on this page that all begin with the letter L, right? We have leukocyte, we have lysosome, we have lymphocyte. And what I find is that sometimes students get these words kind of confused. So be careful you're not getting all these L words confused. Lymphocytes are a type of agranulocyte, which itself is a type of leukocyte. So lymphocytes, there's two varieties of these. And we will encounter these in considerable detail in chapter 13. So I'll just highlight their identity at this time. We have B lymphocytes, which are sometimes simply known as B cells. And B cells are the kind of cells of your body that manufacture antibodies, among other things, okay? So B cells will manufacture antibodies, you know, so if you know anybody that they did have a positive test for coronavirus. It's very likely that their body did make antibodies to the virus, and it would have been their B lymphocyte cell population that actually did that. Okay. In addition to the B lymphocytes, we have the T lymphocytes, which are the T cells. And the T cells are the category of lymphocyte that are responsible for attacking and destroying invaders. Like they will go out and destroy a bacterial cell that's floating in the bloodstream. Or if a virus has infected one of your cells and sickened one of your cells, so it's not a healthy human cell anymore, the T lymphocyte might identify it as a sick cell, and the T lymphocyte might attack it and destroy it as a way of clearing the body of the virus. So think of T cells as sort of the body's assassins to go after abnormal infected cells. Okay, exactly how these cells do what they do, we're going to cover in chapter 13, folks. So, you know, if the story seems unfinished to you, it is. We're going to talk about it in chapter 13. Okay, any questions right now? Okay, let's continue. All right, so that covers, truth be told, as is often the case, right? We don't ever tell you everything. Your book would have to be a lot thicker if we were going to tell you everything we knew. Okay, the kind of white blood cells we've shared with you on page 200 are valid. They are correct, but there are other categories that exist that we're not telling you about yet, and we're going to encounter more of them in the next week. Okay. All right. So the next kind of cell would be the red blood cell. Okay. And you recall that red blood cells are more properly referred to as erythrocytes. Okay. And the function, you know, so up here at the top of your notes, we said that the white blood cells were body defense cells. Red blood cells are not so much body defense cells. What red blood cells are is they are gas transport cells. Okay, their job is to deliver oxygen into the tissue and remove carbon dioxide from the tissue and from the body by moving it back to the lungs so you can exhale it. Okay. Okay, so let's see here. Just a couple things I want to take note of for you with the red blood cell. Okay, question coming through the chat window. What is the name of the special substance that allows red blood cells to transport gases? What's the name of the special substance that allows red blood cells to transport gases? What do you think, folks? Okay. On this one, Nick wins the cup of coffee. Okay. So it's actually hemoglobin. I'm referring to that substance you see in figure 11.4. 11.4. Okay. So red blood cells, RBCs, contain a special compound called hemoglobin, which is critical in gas transport. Okay. Now let's just mention a couple features here. Okay. On average, you know, the measurements that have been taken and the calculations that have been done, on average, each individual red blood cell of your body, on average, has about 280 million molecules of hemoglobin. Okay, think about that. right? We don't have 280 million of anything at our house, right? I mean, perhaps you could say air molecules or water molecules, right? But think about your socks. You certainly don't have 280 million pairs of socks in your dresser drawer, okay? So it's amazing the amount of material that Mother Nature crams into every cell. Each red blood cell contains an average of 280 million copies of hemoglobin. Okay, hemoglobin is a compound. That word compound means something special. The word compound means that there's at least two different things, right? Like if we talked in chemistry way back in chapter 2, we had an ionic compound called table salt, right? Sodium chloride. That's an ionic compound because it's made of sodium atoms and chlorine atoms, okay? So hemoglobin is a compound. And what I'm trying to tell you here is it's made of two different things. Okay, the first I will say is heme. Okay, so hemoglobin has heme in it. Heme is a pigment. Okay. Now don't freak out about that. I mean, you know, from a chemical perspective, pigments are most intimately related to lipids. So when you see pigment, you're thinking about lipid chemistry. But you know, we're not going to do that kind of thing in this course. But the pigment is a lipid. All right. But think about other pigments that are famous that you know about, right? What is the famous pigment for photosynthesis? What's the famous pigment for photosynthesis? Okay, Quinn. Quinn's got it. That's right. Okay, chlorophyll, all right? And think about other pigments in foods that we eat. Think about the carotene that we find in carrots, right? Bugs Bunny's food. Okay, so pigments are more prevalent in our environment than we might initially think about. Okay, so heme is a pigment. And what is important about this pigment is that it contains iron ions. Okay, your book doesn't really give you the chemical structure, and that's okay. If you take A&P, you will get the chemical structure of heme. So heme is a pigment. It contains iron ions that have the ability to bind oxygen molecules. And by oxygen molecules, I mean O2 molecules. Okay? In addition to the heme pigment, hemoglobin also contains globin, right? Globin is not a pigment, it is a protein. Okay? This protein has the ability to bind carbon dioxide. Okay? So what I'm telling you is that hemoglobin is made of two different things, heme and globin, and each of these things combine a different gas. Heme combined oxygen, globin combined carbon dioxide. Okay? But here's something important that you need to keep in your mind. While it is true that hemoglobin can bind oxygen and carbon dioxide, it can only bind one of them at a time. It's one or the other. It's never both at the same time. Okay, hemoglobin can bind oxygen or carbon dioxide, but never both at the same time. Okay? All right. Folks, any questions? Okay. And let me just mention something here that's a common point of confusion, okay, because I see it all the time with my A&P students. Please do not confuse carbon dioxide with carbon monoxide. They are different gases. Okay. CO2 with carbon monoxide, which is CO. Okay, just be careful of that. Okay, folks, do you have any questions right now? All right, let me just mention, just for the sake of completeness, let's just mention the platelets. So that's formed element category number 3, the platelets. Okay, I'm not going to go into detail with that other than to recognize that they exist. Platelets are also known as thrombocytes. And basically they are cell fragments. Cell fragments that help the body form blood clots to stop the loss of blood during injury. Okay. Blood clotting, of which we're not really going to go into, the chemistry. Blood clotting is actually a very complicated topic. There are over 50 distinct, different biochemical steps that the body has to go through to develop a clot. Okay, so if you think about that, if there's 50 different things that have to chemically happen to develop a clot, then for people that are hemophiliacs and they cannot stop the loss of their blood during injury because they can't form a clot properly, that means not all hemophiliacs, not all of them can prevent the loss of blood for the same reason. In other words, there's different versions of hemophilia is what I'm trying to say. There are different ways that the process of forming a clot can be broken. Okay. All right, folks. Just to get our brains turned on here a little bit, let me talk about 2 examples of blood disorders and get you to help me with some things here. I mean, we could do an entire lecture on blood disorders. We could write a textbook on blood disorders, and that's not our goal right now. Okay. Well, let's see about anemia. Okay, anemia. Okay, so first question coming through the chat window. What is anemia? Okay, Nick, you say it's misshaped blood cells. Okay, misshaped blood cells is one type of anemia. I would definitely agree with you. Alyssa, you said it's low hemoglobin. So, Alyssa, you're telling me what causes it, but you're not telling me what it is. Emily, you say having low iron. Again, you're telling me a cause. You're not telling me what it is. Pete, lack of a blood cell. That's a possibility, Pete, but that's a cause. You're not telling me what it is. So most of you are telling me causes of anemia. Okay, okay. Quinn, thank you very much. You're getting there pretty good. Okay, folks, anemia is a disease that is characterized by an inability to carry and deliver oxygen into tissue. That's right. Very good. Okay, now you're getting it. Very good. Okay. Okay, a disorder that is characterized by an inability to deliver oxygen to tissue. That's what anemia is. Now, let's talk about the causes here that some of you mentioned, okay? So let me get Nick's first. Nick, you say misshaped blood cells, so I think you're referring to sickle cell anemia, okay? So sickle cell anemia. Sickle cell anemia, with patients that suffer from this also have reduced oxygen in their tissue because their red blood cells are taking on this abnormal shape, okay? In this scenario, red blood cells have an unusual crescent moon shape, kind of like a sickle, okay? A sickle that you might use to harvest some wheat or something like that, okay? Does anybody know what causes that sickling? What causes the sickling of the red blood cell? Does anybody know? Okay, so, you know, if you look at, say, page 201 of your textbook, you look at figure 11.3, you see these beautifully magnified red blood cells. They all basically look like a nice circle there. They have a nice round shape to them. Okay, a sickled red blood cell is not going to have that shape. It's going to literally look like a crescent moon shape that you might see, you know, a partial moon in the night sky. Okay, the sickling of the red blood cell is due to an accumulation of a mutated form of hemoglobin. Due to an accumulation of a mutated form of hemoglobin. Okay, and folks that have sickle cell anemia, you remember right up here that globin is in fact a protein. Globin is a protein. Folks, what are proteins made out of? What are proteins made out of? Okay, good. That's what fantastic. Makes me feel good that you can answer that quickly. Okay, proteins are made of amino acids. In the globin protein, there is a mutated amino acid caused by a mutation in the DNA at a single nucleotide position. I forget the exact one off the top of my head, but there is one biochemical nucleotide letter that is altered in the gene for globin that results in a mutated globin protein, which results in a mutated hemoglobin compound, which causes the actual cell to develop an unusual shape. And the reason that this is so problematic for delivering oxygen to tissue is because when these cells take on a crescent moon shape, they cannot get through the capillary beds properly. They kind of get gummed up. They get stuck inside there, like kind of like too many people trying to get through a narrow door at the same time. Okay. So let's see here. Sickling of red blood cells due to an accumulation of a mutated form of hemoglobin. There is a single nucleotide mutation in the gene for globin that leads to a mutated protein, which leads to mutated hemoglobin, which leads to sickled cells. All right, so that's actually, I mean, I actually don't know what the prevalence of that is in society. It's fairly low compared to other diseases, but still, if you have it, it can be quite serious. And it's also quite painful too. Okay, why do you think sickle cell anemia would be painful? Why is sickle cell anemia painful? Right, you might think, okay, you don't have enough oxygen, so you feel tired. That would be an obvious thing, right? You don't have enough oxygen. But why the heck is it painful? Okay, well, it comes back to my earlier statement, folks. When the red blood cells take on an unusual shape, they can't get through the capillary blood vessels very well. They get gummed up. And what happens is that the blood vessel begins to swell, starts to get larger because of all these blood cells that can't get through. And when the blood vessel swells, nerve endings that are attached to the wall of the blood vessel will generate an action potential of pain that goes up to the brain, and you feel it. Okay, so when the blood vessels swell in an unusual way, that generates pain signals. Okay, so back to the causes of anemia. Many of you said, excuse me, many of you said that, okay, so there's some other things here that you said could cause anemia. So, okay, so a low blood level could do that, right? So blood loss, obviously that could be to trauma of the body. You were in a car accident and you lacerated your femoral artery. That would be very, very bad. Okay, or it could be, you know, the normal natural process of menstruation that women go through. Okay, that could cause the blood loss leading to anemia. Some of you talked about, well, okay, Matt, you said a lack of hemoglobin. I could agree with that, because, and that would suggest, you know, that would suggest potentially another genetic disease, because if you don't have enough hemoglobin, maybe it's because of not enough hemoglobin is getting manufactured. So it could suggest another genetic defect. Okay. Catherine and Emily, you mentioned low iron levels. Okay, so let's talk about that a little bit. Okay, so my question to you, and feel free to type into the chat window, what could potentially cause a low iron level? Well, certainly blood loss could do that, right? Trauma or menstruation could be the reason that your iron level is low. That's a possibility. Okay, but what could lead to problems with low iron? Okay, so all right, so Catherine, you mentioned diet. Okay, so right, we might have a poor diet where we're not eating enough foods rich in iron. That's a possibility. I mean, that cannot be discounted. Typically in the United States, that's usually not an issue, because typically in the US, we have the opposite issue where we have too much iron in our bloodstream, particularly if you are a meat eater like I am. Typically our iron levels are higher than they really should be. Okay, but yes. Okay, Alyssa, an absorption issue. I like where you're going with that. Okay, it might be a situation where you are eating enough, you are eating sources that have a lot of iron, but for whatever reason, you're not absorbing it properly. Poor absorption of iron, and this could suggest an issue with the small intestine. Catherine, do you have a specific thing in mind when you say thyroid issues?
Not specifically. I know I am slightly familiar with it can lead to iron issues.
Okay, thank you.
Depending on what the thyroid issue is specifically.
Absolutely, absolutely, right. The thyroid produces a number of hormones that are involved in regulating the overall metabolic rate of your body, which can influence how rapidly you do or do not absorb substances, including iron. So it could be a thyroid issue. Okay. Anything else you might think might be a problem with low iron levels? Let me throw another one out there that folks often don't think about. In fact, I'll share a quick story with you. But it's possible to have low iron levels because you have an infection. Okay. 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 Quick little story here. One of the gals that I work with, it's probably going on close to 10 years ago now. Her son at the time was anemic. He was about 17 or 18, so her son was anemic, and obviously it's not normal for an 18-year-old male to be anemic. I mean, that's not what we expect to be the case. So she took him to the doctor, and they ran a bunch of blood tests and did a bunch of investigations on him, thinking about whether he has, some form of blood cancer or something like that. All kinds of different things they were doing. This took several months of visits and testing and so forth, and they could not figure out why this young man was anemic. And so finally, the doctor sort of threw up his hands and said, okay, he said, well, we don't know what's causing this, and I have no proof, but I'm still going to prescribe an antibiotic because it's possible that your son has a subclinical undetectable infection of some kind that's robbing his body of iron. And sure enough, 2 or 3 weeks after being on the antibiotic, he was no longer anemic anymore. So he did have some kind of microbial infection in him that was scavenging the iron in the bloodstream. And we do know that bacteria in particular release substances that are called siderophores. Don't worry about it. You won't get tested on it in here. But bacteria release these compounds known as siderophores that have the ability to bind oxygen in the bloodstream and keep it away from your red blood cells. And that can cause you to become anemic. Okay, so my point here, folks, is anemia is this disorder characterized by an inability to deliver oxygen, but you can quickly see that the inability to deliver oxygen can have many different causes. And that's really the hard part when you treat disease, is figuring out what the heck is the cause. You might treat a symptom to make a patient more comfortable, but unless you figure out the cause, you're not going to get too far. Okay.
I did have a quick question before you go on.
Okay.
How would a bacterial infection like that not be detectable, especially if it's causing anemia, where it would be, pretty much starving the entire body out of oxygen? So that means the body's pretty well infected with said bacteria.
Okay. When I say it's not detectable, Matt, what I mean is it's not detectable by standard means of investigation. There certainly are more types of bacteria, more species of bacteria on our planet Earth that we do not know about than we do know about. So how do we detect things we don't even know exist yet? That's sort of the issue. Another aspect of this is that it's also possible that the bacterium could be infecting the body, but the patient's immune system is able to kind of hold the bacterium at bay long enough in sort of this internal struggle, this internal tug of war, so you don't ever really get over the top sick, but you just kind of get mildly sick. And so that seemed to be the case with the gentleman I was talking to you about.
I understand. It's kind of almost like the bacteria is being parasitic in a way, where it's not trying to be detected, but it's still hurting the body in some way.
Yes, absolutely. Absolutely. Okay. I mean, I would imagine there are millions of people around the globe at this time that probably don't feel terribly well, but they don't feel bad enough to go to a doctor, and it might be a subclinical infection, right? Their body's kind of battling something and keeping it at bay so that they don't get a full-blown disease, but they just kind of feel a little bit less than they should feel. So at any rate, there was something else, but I can't think of what it was I was going to say. So anything else about that you'd like to talk about? Okay. folks, any other questions about anemia? All right, let's just mention one final thing here as leukemia. Okay, now obviously I think you all know, I mean, you've all heard of leukemia. Hopefully you don't know anything about it from a personal perspective. I mean, I've known, unfortunately, I've known some children in my life that developed leukemia. Not cool at all, right? So leukemia is a cancer of the white blood cells. Right, and our understanding of cancer is still very, very much incomplete. Way too many people die every year of a variety of different cancers that we just cannot control properly. Okay, so there's a lot we don't understand. But what I wanted to bring out here is that obviously, you know, if you have a cancer of the white blood cells, and that means your body's defense cells are sickened. So not only are you dying because of cancer, but you are potentially dying because all of a sudden your defense cells that should be able to defend against the cold virus aren't able to do that, or will not do that because of their altered disease state. Okay, so it's very problematic from that perspective. The other thing that I might as well mention here as well, since we're talking a little bit about cancer, is that, you know, from the conversations we've had, that your red and white blood cells develop from stem cells, adult-derived stem cells in your red bone marrow, and you again highlight that on page 201 of your book. Okay. There's a connection here that's very important that scientists probably started thinking about in a serious way about 20 years ago. Okay, so let me just put this down. Remember that red and white blood cells come from adult-derived stem cells in the red bone marrow. Okay, what scientists, you know, we all at various moments of our life have what are these, you know, these light bulb moments where something starts to click and you're like, oh, that's what's going on. That's what is happening. I finally understand osmosis, right? Okay. Well, a light bulb moment for scientists about 20 years ago was the realization that cancer cells and stem cells seem to have very similar properties. Okay. Scientists realized about 2 decades ago that stem cells and cancer cells share some important properties. Okay, but probably the most notable of these is that stem cells are virtually immortal. Okay, what I mean by that is that a stem cell that's in a healthy environment and given food can grow and reproduce new cells basically indefinitely. Those stem cells don't wear out and they don't die. Okay, if you take stem cells out of the body and put them into basically the equivalent of a petri dish, and you feed them and everything properly, they can grow and reproduce many, many, many times without wearing out. A normal cell of your body that's not a stem cell, such as a skin cell or a cardiac muscle fiber or anything else, you put it in the lab and give it some food, it'll grow and reproduce maybe 10, 20 times, but then it basically peters out and dies. So it's not immortal. Stem cells are virtually immortal, and so are cancer cells. Both types of cells can reproduce indefinitely in the research lab. Okay? And so it was this primary observation that began to make scientists think that at least some forms of cancer are actually diseases of the stem cells in the body. The observation above led scientists to consider that at least some cancers are really diseases of the stem cells, okay? Now, obviously, that's extremely important because we know that stem cells are the cells that kind of repopulate our body. You know, anytime you skin your knee by falling on the macadam, you'll develop a scab and you'll get fresh skin tissue there given enough time to heal. That's because the stem cells in the dermal layer of your skin are able to reproduce themselves and you repair yourself. But what we're saying here is in a disease like leukemia, which is a problem of the white blood cells, which is probably a problem in many cases of the underlying stem cell, right? This is so very difficult because if you have the stem cells that are responsible for maintaining the integrity of the immune system, if those stem cells are themselves diseased and going to die or cause death of the other cells, well, then things are looking pretty bleak, right? And that's why a lot of times leukemia patients may need a bone marrow transplant to kill off the diseased stem cells creating the leukemia and replace it with fresh stem cells that are not unusual or abnormal in some way. Okay. Folks, any thoughts or questions at this time? Okay. All right, folks. You know, I really do, you know, cancer is a devastating disease, but you young folks are going to live in a time where better than ever, we have the ability to deal with it and manage it. Of course, we do have the sticky societal issues of exactly how we pay for that treatment, but, you know, you're going to live in a time where the treatments that exist are just going to be amazing. Okay. Let's continue here. Last topic that I want to talk is your blood types. Okay, blood types. And so this is a topic that goes to page 206, 207 of your textbook. And I'm going to be talking about it in the context of a PowerPoint drawing. So I'm just going to reference that in your notes here, blood types, see PowerPoint drawing. Okay, and so many of you did a pretty good job with the lab write-up. Most of you answered the blood typing information correctly. But let's just go over that again because there's some nuance there that I would want you to appreciate a little bit. Okay, so bear with me just a moment. And at this point, you should now see a PowerPoint screen, okay? And we are going to talk about blood types. And what I'm going to do here is take this sheet of paper, this virtual sheet of paper in the PowerPoint window, and I'm going to section it into 4 sections. Okay. Now, there's actually different categories of blood typing technology. We're going to be talking about the A, B, O blood types. And so I'm going to draw a circle in each section. That circle is to represent a red blood cell. Okay. So yes, these are red blood cells, RBCs. Okay. And you know that the red blood cell obviously is floating around in the blood, so that's the plasma, right? So everything around here is in fact the plasma. Okay, you know from your own reading and your homework that you did for me that we have type A blood type, we have type B blood type, we have type AB, and we have type O. Type O, there's actually no surface molecule there, so I'm not going to draw anything coming off the surface. This is going to be type O. Okay. All right. So just some things that I think you're familiar with, but okay. So these molecules hanging off the surface of the plasma membrane of the cell, they're referred to as antigens, okay? So this is the A antigen. And then we have the B antigen. Okay, and then in the next cell, we have the A and B antigens. Type O, there are no surface antigens. Okay, so is anybody able to tell me what an antigen is? Can anybody tell me what an antigen is? Let's type that word up here with a question mark. What's an antigen? What's an antigen? This is a word that we probably didn't encounter in our course yet, and it's really something that's going to come into its own in chapter 13 about 2 chapters from now. What's an antigen? Pete, you say antibodies. Okay. They are not antibodies, Pete, but you're getting started thinking. I appreciate that. Alyssa, you're right. It's a molecule. What kind of molecule is it? Where do these antigens come from? Okay, to help us move forward here, folks, an antigen is a substance. Quinn, you say, does it involve bonding? Well, it could, depending on what you're talking about. They may come from DNA, that I would agree with, okay? Folks, an antigen is a substance, so it's a molecule, Alyssa, that is manufactured when the immune system becomes activated. An antigen is a molecule created when the immune system gets agitated. Let me define that differently, folks. Sorry about that. If you start writing that down, scratch that out because I misspoke a little bit. Folks, an antigen is a molecule that does the agitation. It's a molecule that activates the immune response. A molecule that activates the immune system, right? So if you have a bacterial cell that infects you, some of the molecules hanging off the plasma membrane of the bacterial cell would be antigenic, meaning they would be agitative to the immune system. The immune system would respond to their presence. Okay, so we have antigens, molecules on the surface of our red blood cells in some cases that actually activate the immune system. At any rate, these antigens, okay, these specific antigens, these ABO antigens, they are made of glycolipids, right? The A antigen is a glycolipid. The A antigen is a glycolipid, the B antigen is a glycolipid. All I'm doing is telling you that it is a molecule made of a carbohydrate attached to a lipid. That's what it is. Today, we do know the chemical structure. It's big, long, and complicated, so I'm not going to draw that out. But these A antigens are made of glycolipids. If you have the A glycolipid, you are type A blood type. If you have the B glycolipid, you are type B blood type. If you have A and B, you're type AB. And if you don't have either of these glycolipids, you're type O or type 0. Now, the antigen is a molecule that activates the immune system. And what you notice from reading your own book is that if you have type A blood, then in the bloodstream, in the plasma, you are going to have, let me give it a different color here, you are going to have anti-B antibodies floating in the plasma. Anti-B antibodies. If you are type B, you're going to have anti-A antibodies in the plasma. If you're type AB, you have neither anti-A or anti-A antibodies, so no anti-A or B antibodies. And if you're type O, you're going to have both anti-A and anti-B antibodies. Okay, so the antigens are molecules that activate the immune system. Okay, they activate the immune system, and one of the things that occurs when you activate an immune system is that you get antibodies being manufactured. So, you know, we have these anti-B, anti-A antibodies floating around in some of the plasmas of the different blood types. But there's a mystery here. Okay, there's a mystery here. If you have an A antigen, one would predict that you actually develop an anti-A antibody in the plasma, not an anti-B antibody. That seems to be counterintuitive. Okay, so here's the question coming through the chat window. Why does a type A blood type have anti-B antibodies in its plasma? Why does a type A blood type? Okay, Quinn, you have an interesting answer there. So it doesn't harm itself. That's true. If you had an A antigen, if you were blood type A and you had an anti-A antibody in the plasma, that antibody would bind to the antigen, and that would cause you harm. So that's a very practical answer there. And I could say that's a good answer, okay? But my question is more of, well, what's the source that generates the anti-B antibody? Okay, what causes the anti-B antibody to be made in a type A blood type? What causes the anti-B antibody to be made in a type A blood type? Okay, I'm challenging you a little bit. I'm picking at you a little bit. But folks, the answer is we do not know. Nobody in medical science knows the answer to that question, which again highlights the reality that there are many things we don't have comprehensive knowledge on yet. Okay, so the answer to my question is we don't know. We do not know. And there's nothing shameful in that, right? The first part of science is asking a question and saying, well, how does that work? Most likely you don't know how it works, and we still don't know how it works. I will say this. One of the leading ideas for the presence of the antibodies in the plasma, and it's just an idea, it's never been proven. One of the ideas is that you may or may not know that it is frequently true. It is frequently true that babies are born without any antibodies in their blood plasma. So a type A baby is born without any anti-B antibodies. But 2 months later, that baby is going to have anti-B antibodies. So the antibodies develop after birth. And so the thinking is this, that a child may be exposed to something either by the birthing process itself. So for example, as the child comes through the birth canal, it's being exposed to microorganisms it was not exposed to in the uterus, and it's being exposed to microorganisms outside its normal environment. Once it's outside the mother's body, it may be the presence of bacteria or other microorganisms in the environment that actually stimulates the production of the antibodies. Because what scientists have observed is that some bacteria do have antigens that would seem to trigger this kind of response. I mean, it's been tested in the lab, okay? So we're really not sure exactly how this happens or even necessarily why it happens, but an idea is that as you are born, you are exposed to microorganisms, which creates the immune response, leading to the development of these anti-A and anti-B antibodies. Okay, questions so far? Okay, let's continue here. There's another related idea, and Quinn's answer kind of highlights something here. There's a phenomenon that can happen when you mix incompatible blood types called agglutination. Okay, agglutination, which you see on page 206, right? The term agglutination is along the right side of figure 11.7. Agglutination is when the blood cells start to clump together. Technically speaking, agglutination is not the same thing as blood clotting. They are not the same thing, although it might seem like they're the same thing. But agglutination is not equal to clotting. Okay, they are biochemically distinct from each other. But at any rate, agglutination does refer to a clumping of red blood cells. right? So let's say, for example, God forbid, that you're in a car accident and you have some blood loss and you're a type A blood type, and in the chaos of the emergency room, someone begins to transfuse you with blood type B. So you have blood type B going into the body of the person there, right? That's going to create agglutination because the anti-A antibodies are going to come over and lock onto the A antigens, and the anti-B antibodies are going to go over and lock onto the B antigens on the other cells. Okay, that's going to cause the clumping that I'm referring to, which is known as agglutination. Okay, folks, please tell me what picture of figure 11.C is showing you agglutination. What picture of figure 11.7 is showing agglutination? Folks, what picture of figure 11.7 on page 206 is showing agglutination? Okay, thank you, Emily. C, the bottom picture, and B as well, right? Both B and C, the bottom pictures, are showing you agglutination. I just want to be sure that you're all looking at the right pictures in your textbook. Okay, so one last thing, or maybe two last things, okay? If, you know, I'm sure you have heard over the years, for example, I'm sure you've heard that type O is the universal donor, right? Type O is the universal donor. Okay, so I'm going to ask a question through the chat window. Here's my question coming through the chat window. Will there be any agglutination if you transfuse type O blood into the body of a type B patient? Okay, will there be any agglutination if you transfuse type O blood into the body of a type B patient? Okay, Quinn, thank you. You say yes, but not as much because type O has no surface antigens, but type O has both antibodies, I think you say. Okay, Pete, you say it depends. So is there something more you want to say about that, Pete? Okay, so what I'm trying to point out to you folks is that you never want to look at words and just blindly accept them, right? If you say type O is a universal donor, you might say, oh, okay, so you can give it to anybody, there's never a problem. There's never a problem, and that's not true, right? With the type O universal donor scenario, if you give type O, then these anti-B antibodies are going to go over here and bind to the B antigen. That's going to create agglutination. If you were to give type O to a type A patient, the anti-A antibodies would then go over here and bind to the A antigen, right? And that would create a problem there. So the universal donor is really not completely free of danger. Okay. So another question. What would you have to do to type O blood to make it a true, meaning completely safe, universal donor? That's right, Quinn. You would have to have no anti-A or B antibodies. And to achieve that, what you would have to do is separate the plasma from the red blood cells. That's my point. For type O to be a true universal donor, you have to separate the blood cells from the plasma. That can be done in the clinical laboratory. In fact, hospitals do it every day. Okay? But God forbid, you're on a battlefield somewhere and your buddy needs a blood transfusion and you know you're type O blood and you try to do a battlefield transfusion, you're going to be transfusing the blood cells in the plasma. There is a possibility of agglutination which could harm your buddy. Okay? So universal donor is only a true universal donor when you donate the red blood cells.
Isn't there, the one thing I always understood is there's a difference. There's O negative and O positive. This with every other blood type as well. And I know with type O being universal, isn't, I forget which one, is it negative or positive?
Okay, so let me.
Doesn't that come into play?
Okay, who's speaking right now?
Catherine.
Catherine, thank you. Yeah, Catherine, I'm not going to test you on this, but I'll answer your question. When you talk about the positive and negative business, I'll just draw a little note down here on the bottom. Positive and negative is referring to the RH factor, which I believe your book does mention here. It does talk about the RH factor on page 207. So let me make a note of this. RH factor. Okay. The RH factor is symbolized by what is known as the D antigen. Okay, let me make it a different color so you can see it better. D antigen. Okay, so Catherine, if I put the D antigen out on the surface of the blood of type O, then that would make it type O positive. Okay? If I have no D antigen on the surface of the AB blood type, then that would be AB negative. Okay, so if you have the D antigen, that makes you Rh positive. If you don't have the D antigen, that makes you Rh negative. Okay, and it simply refers to the presence of a different molecule that if you have it, you're positive. If you don't have it, you're negative. That also can play a role in blood transfusions. And as you may well know, it also is important during pregnancies to monitor that to make sure you don't have a bad response of the mother's body to the growing baby inside the womb. That's what figure 11.8 on page 208 is trying to talk to you about. The RH factor is named after rhesus monkeys, where these molecules were first identified in. Is there another aspect of that, Catherine, that you were wanting help with?
Well, the one question I had specifically is when you're talking about type O, my understanding is, and I forget which one, O positive is a universal donor, or type O negative.
Yeah,
I don't think it is type O period.
Yeah, it's type O period, right? It doesn't matter. It doesn't matter about the positive and negative business, okay? Type O is the blood type that's called the universal donor, but as I'm suggesting, it's not really a universal donor unless you're only donating the red blood cells. Because if you have any antibodies in the plasma that get transferred to a patient, that can create some level of dangerous agglutination. Okay. Okay, so Nick, you had a question. So why can't A be used if they already have no antibodies? That's a good question. Okay, so let's say I take, all right, so to answer Nick's question, type AB is often referred to as the universal recipient. Okay, universal recipient. Okay, so if I put type A blood into the type AB patient, obviously type AB has no antibodies to cross-link to the antigen on the donated blood. But the donated blood will have an antibody against the surface antigen on the type AB blood cell. So that also is not 100% safe, Nick. Does that make sense? Okay, right. So really what I'm trying to do, folks, is caution you a bit. You know, it's like, and I'm as guilty as anybody, right? We read words and we assume they mean exactly what they mean, but everything is contextual. Universal donor is not a true universal donor if you're donating plasma with the cells. Universal recipient is going to have the same problem, okay? So you need to be careful about not extending these ideas to ridiculous extremes. Okay. Other questions? Okay, folks, do you have any questions about chapter 11? Because I'm going to be starting the next chapter here if you don't have questions. Okay, all right, I guess your folks are okay. So let's call a rest to this chapter and let's get started with chapter 12. Okay, so I'm going to go back to the Microsoft Word document. And we're going to start talking about the circulatory systems. Okay, so chapter 12 starts on page 213, 214 of your book. Okay, when we talk about circulation, there's multiple things we could talk about. Okay, two broad categories here. The first is, in fact, the cardiovascular circulation. Which truthfully, we're going to spend most of our time on that topic for chapter 12. You know, all of these topics are too meaty for us to really get comprehensive coverage here in this short 8-week class. Cardiovascular circulation, when you talk about the cardiovascular system, you're talking about the system that's responsible for the movement of blood. I think we can appreciate that. And then there's the lymphatic system, which is responsible for the movement of lymph fluid. Okay. Now, I'm not going to talk too much about that, but you will certainly encounter it in the reading of chapter 12. Let's put this question into your notes. What is lymph fluid? What is lymph fluid? Can anybody answer that? What is lymph fluid? The lymphatic circulation, or the anatomy of the lymphatic circulation, is actually highlighted at the end of this chapter, page 228. If you do have access to your book, please take a look at page 228. You see figure 1217. You see the anatomy of the lymphatic system. Folks, just so we don't get bogged down here, the lymphatic fluid, the lymph fluid, is actually filtered blood plasma. Okay, so lymph fluid is filtered blood plasma. Okay, it might seem like an odd idea, but it is definitely true that every time your heart contracts and it pushes blood into arteries, okay, a little bit of that blood plasma that are in your capillary beds leaks out of the capillary beds. When it leaks out of the capillary beds, it becomes interstitial fluid. It's basically plasma that has left the vasculature. That interstitial fluid, if it just stayed there, you would develop edema. And you'd have your body parts swell. I'm sure you've seen people walking around the grocery store that have swollen legs and things because they have a problem with their circulation. That's edema. Okay? Well, long story short, that blood plasma leaves the capillaries, it becomes interstitial fluid, and then that interstitial fluid gets drawn up into the lymphatic vessels of the body. And when it gets into the lymphatic vessels, it's now called lymph fluid. Okay, so the lymph fluid is plasma that has left the blood vessels and is now traveling in the lymphatic vessels that you see on page 228 of your textbook. Okay. Now, another question. What is the purpose of blood plasma leaving the blood vessels and moving into the lymphatic circulation? What's the purpose of it? Okay, this seems all kind of weird and foreign to us, but especially if you haven't read your book on this yet. What is the purpose of blood plasma leaving the blood vessels and moving into the lymphatic circulation? What's the whole point, gang? Anybody? Okay, Pete, to cleanse the blood, that's not a bad way of thinking. And Quinn, you mentioned about keeping it clean. That's also not a bad way of thinking. Alyssa, to transport fat, that's a very good idea, Alyssa, and some fat transport does take place in the lymphatic circulation. That's a good answer. But what I'm fishing for is basically hinted at by Quinn and Pete's answer. You notice, if you are able to look at the pictures on page 228, that the lymphatic system has these things called lymph nodes. Lymph nodes. And I bet you, if you've been sick, you went to a doctor and they pressed around your neck or your armpits and things to see if your lymph nodes were swollen. Okay, so the point of moving blood out of the vasculature and into the lymphatic circulation is to check whether there are microorganisms and dangerous substances in the blood that need to be handled by the body's defense, by the immune system. So think of it as a way, not necessarily of cleaning the blood, but of alerting the immune system that something dangerous is present. Okay? To perform a quality control check on the blood plasma to identify potentially dangerous substances, potentially dangerous microbes. Okay, the whole point is so that we can alert the immune system to a potential problem and hopefully handle the problem before it overwhelms us. Okay. All right, gang. So that's the lymphatic system. I'm not going to really talk about the anatomy of the lymphatic system, but I am going to talk about the functioning of the immune system in chapter 13. So we're not going to ignore this topic, but I'm going to talk about it in chapter 13. Okay, folks, any questions right now? Okay, so let's spend the bulk of our time from chapter 12 talking about the cardiovascular circulation. And first off, we need to define the basic anatomy of a typical blood flow loop. I'm going to use words that I bet you already know. I mean, one of them is the heart, right? You know the heart. But the thing of it is, do we understand how it all fits together? So let's talk about the anatomy of a blood flow loop, okay? And for this, you can be looking at page 215. All right. So no surprises here. We'll just define the basic anatomy. First is the heart. You know, the heart is a muscular organ that contracts and it pushes blood through your blood vessels. That's a little imprecise. When the heart contracts, it always pushes blood into an artery. It never pushes blood into a vein. Muscular organ that contracts to push blood into an artery. Okay. If you've studied any heart anatomy, you know there's actually a left side to the heart and a right side of the heart. There's actually two pumps. The heart is an organ that's made of two pumps, the left pump and the right pump. The left pump is responsible for most of your systemic circulation, and the right pump is responsible for your pulmonary circulation. It takes blood to and from the lungs. We'll talk about that in just a moment. Okay. Next, we have artery. Okay. Arteries are the largest blood vessels of the body, largest in terms of diameter, not length. Largest blood vessels of the body that always carry blood away from the heart. Okay, they always carry blood away from the heart. Now, arteries will become, we think about, if you've ever looked at a giant map of the United States, you can see all the roads and it looks like a giant jumbled cobweb of roads and things. Well, we basically have a cobweb of blood vessels in our body as well. And so the largest vessels that carry blood away from the heart are called arteries. If we have a smaller or medium-sized blood vessel that also carries blood away from the heart, we'll call it an arteriole. Okay. Medium-sized blood vessels. They're basically tiny arteries that also carry blood away from the heart. Okay, the arterioles are always going to dump into a capillary, which is typically part of a network of capillaries called a capillary bed. So the next blood vessel is that darn word capillary, which has come up when we've talked about, sickle cell anemia and other conversations we've had in class. Capillary is the smallest blood vessel of the body. And capillaries, which are part of capillary beds, right? If you look on page 217 of your book, page 217, you see figure 12.4. You can see the capillary bed there in the top picture. Okay, it's a spider web network of tiny, tiny blood vessels. And by the way, since it's relevant, figure 12.3 shows you a capillary with red blood cells moving single file through that structure. Capillaries are so tiny that even blood cells, which are also tiny, have to go through single file. That's how tiny a capillary is, okay? So small that RBCs must pass through single file, okay? And obviously, if you do have sickle cell anemia and the cells get jammed up, they just can't get through the capillary. Okay, so the capillaries are parts of networks called capillary beds, okay, which are marketplaces of exchange. I'm going to say it that way. They are marketplaces of exchange, okay? And what I mean by that is, think about the last time you've been to a farm market, you know, maybe Roots or the Green Dragon or wherever you like to shop. You know, you go to a farm market, you find some cantaloupe or some green beans that you want. So you give a person a few dollars and they give you a carton of green beans, okay? So there was an exchange. You gave money, they gave you a vegetable, okay? Capillary beds are marketplaces of exchange. Now, we're not handing over literally green beans, although we could be handing over the nutrients from the green beans. But what I mean is that in the capillary beds, the body has an opportunity to deliver oxygen into the tissues of the organs of your body so that they can perform aerobic cellular respiration to create ATP so that you can continue to live. At the same time, you know from our conversation in chapter 3 that aerobic cellular respiration will create waste products, one of which is carbon dioxide. That carbon dioxide can be put back into the bloodstream at the blood that's in the capillary beds. And then that blood can move away, ultimately getting to the lungs so the CO2 can be exhaled out of the body. So that's what I mean by a marketplace of exchange, okay? Oxygen, O2 can be O2 and nutrients can be delivered into tissue, while CO2 and waste can be removed from tissue. All of that exchange of cargo is going to happen in the capillaries that make up capillary beds. Okay. All right, folks, please stop me if I'm going too fast or if you have questions. Next, the capillaries, okay, once you've had an exchange of cargo there, you know, there'll be a brief pause in time so that material can move back and forth across the cells there. Then the blood's going to continue its journey back to the heart. And at that point, the capillary is going to link up with a medium vessel called a venule that always delivers blood back to the heart. So a venule is a medium-sized vein that always moves blood back toward the heart. Okay. The venules will then merge and form larger vessels, which are the veins that will then move blood directly into the heart. Largest, again, in a diameter sense, blood vessel that moves blood toward the heart. Okay? All right. Okay, so that's the basic anatomy, and now what we want to do is see how it's all connected, and to do that, I'm going to go back to PowerPoint and talk about a blood flow loop, and just highlight in your notes that you should consult the PowerPoint drawing. Okay. Any questions before we leave the note-taking screen? Okay. All right. Let's go back to PowerPoint. And just a moment here. Okay. All right. So, okay. So we're back at PowerPoint. I'm going to insert a new slide. Okay. And we're going to talk about a blood flow loop. Okay, so you'll have to humor me again because you know I really cannot draw worth a darn. So I'm going to draw your heart as a Valentine's Day heart. Okay, there's your heart. Magnificent. Okay. Now, to illustrate the principle, we got to have some other reference anatomy. So just to blow things up here, I'm going to put in your lungs as rectangles. Okay, so here's your lungs. And I'm going to put a rectangle below the heart, which will just identify as your abdomen. Right, so your intestinal tissue, that kind of thing. So, if we have blood, okay, if we have blood leaving the heart and going to the lungs, if we have blood leaving the heart and going to the lungs, okay, my first question to you is, if the blood is leaving the heart, if it's leaving the heart and going to the lungs, what cardiovascular circuit is the blood in? Okay, thank you, Nick, for answering, and I appreciate you answering. That's not correct, so it's good we're talking about this. What is the name of the cardiovascular circuit that the blood is in? What's the name of the cardiovascular circuit that the blood is in? What blood circuit is the blood in? Okay, Emily, thank you. You fired for us correctly. It's in the pulmonary circuit. Okay, so let's put that up there. Okay, pulmonary circuit. The pulmonary circuit is the cardiovascular circuit that moves blood to and from the lungs. To and from the lungs. Okay, so right now, the blood has left the heart, it's going up to the lungs, so we are in the pulmonary circuit. Okay, we're in the pulmonary circuit. Okay, here's my next question. Is the blood in an artery or vein? Okay. All right. Okay. Remember, folks, yes, okay. All right, good. We're doing this, right? There's presenting the information, there's memorizing it, and then there's applying it, right? Okay, the blood is moving away from the heart as it goes towards the lungs. So that's going to be an artery. So right now the blood is in a pulmonary artery. The blood is in a pulmonary artery. Okay. And my next question coming through the chat window. Is the blood in that pulmonary artery oxygen rich or oxygen poor? Is the blood oxygen rich or oxygen poor? Okay, Quinn says it's poor. Do you agree with her? Do you agree with Quinn that the blood is oxygen poor? Okay, Alyssa agrees with you, Quinn. That'll satisfy me. I agree with you too. The blood is in fact oxygen poor. You have to think, why is the blood moving to the lungs? The blood is moving to the lungs to get rid of CO2 and in the next moment allow you to inhale fresh oxygen in the air around you. So that blood is low in oxygen. It's low in oxygen and it is high in carbon dioxide. All right, so this blood is O2 poor and it is CO2 rich. Okay, question coming through the chat window. Where does the CO2 come from? Okay, where did the capillaries get it, Quinn? Quinn says the CO2 comes from the capillaries. That's not wrong, but I'm trying to drive to a slightly different area. Okay, other tissues during cell respiration. Okay, from your cells after ATP or during ATP production. That's what I'm after. Very good. Okay, the CO2 is a waste product of aerobic cellular respiration, right? Waste from ACR, aerobic cellular respiration. Okay, very good, folks. Then we can go a little bit quicker here now. Okay, so the blood leaves the heart, goes to the lungs. In the lungs, there's going to be capillary exchange. Okay, we'll just put that in as a dark green, I guess. So there'll be an exchange of gases. Exchange of gases. Okay, exchange of gases. That means that CO2 is exhaled out of the body. Oxygen is inhaled into the body at the lungs. Okay, so there's an exchange of gases in the capillary blood beds of the lung tissue itself. Next, the blood will continue its journey and it will continue back towards the heart. Okay, so somebody answer my question. As the blood leaves the lungs and goes to the heart, what circuit am I in? As the blood leaves the lungs and goes back to the heart, what circuit am I in? Okay, Emily, good job. All right, we're back in the, we're still in the pulmonary circuit. Is the blood vessel an artery or a vein? Is the blood vessel an artery or a vein, folks? Okay, Quinn, you're right. It is a vein because they're going back towards the heart. The blood that's in that pulmonary vein, is it oxygen rich or poor? Okay, good, Alyssa and Quinn, very good. Okay, so we are oxygen rich. Why are we oxygen rich? Because we just inhaled oxygen out our lungs. And if it's oxygen rich, then it's also CO2 poor because we just unloaded carbon dioxide at the lungs. Okay. Now, obviously this is not drawn anatomically correct because I can't do that for you, but you get the idea that there is a left and right side pump to the heart. The right side pump is responsible for the pulmonary circuit that you see right now. Okay, so this is going to be the right side of the heart. Okay, and in contrast that, and at the same time simultaneously, the left side, the left pump of the heart is going to be working to deliver blood through the systemic circuit. Okay, the systemic circuit moves blood to and from all tissues of the blood, to and from all tissues of the body other than the lungs. To and from all body tissues other than the lungs, and that's going to be the left side of the heart. Okay, so let's finish our little cartoon drawing here. Okay, the blood that has entered the heart from the pulmonary vein is then going to be shunted out to other areas of the body. The abdomen being my example of a system, okay, of a system. So this blood here is going to be in the systemic circuit. And because it's leaving the heart, it's going to be an artery. The oxygen is still rich because it came from the pulmonary vein. And the CO2 is still poor. Okay? Please stop me if you have questions. So that blood reaches the tissue of the abdomen. There's going to be gas exchange as well in the capillary beds. Okay, there'll be gas exchange there. And then the blood will leave those capillary beds in the abdomen and start its journey back toward the heart. That will also be the systemic circuit. But now it's going to be a systemic vein because we're delivering blood back into the heart. Because the oxygen was unloaded to the tissue of the abdomen, that blood in the systemic vein is oxygen poor. And the CO2, which was picked up in the capillary beds of the abdomen, is going to be CO2 rich. Okay? All right. Gang, do you have any questions about that? Does it make sense to you? Okay. Any questions before we leave our little cartoon drawing here? Okay. So when we talk about circulation, you have lymphatic circulation, okay, which moves the lymph. You have cardiovascular circulation, which moves the blood. And there's actually subdivisions or subtypes of cardiovascular circulation, which are referred to as circuits. Here we have the pulmonary circuit, which is that type of cardiovascular circulation that moves blood to and from the lungs. And we have the systemic circuit, which is that subtype of cardiovascular circulation, which moves blood to and from all the tissues of the body except the lung. Now, there's some additional things, you might talk about in a more advanced course, such as coronary circulation. That's circulation that feeds blood into the heart muscle itself. Coronary circulation is a subtype of systemic circuit circulation. Any questions? Okay. All right. Hopefully everybody is with me here. So let's go back. In the few minutes we have left, let's go back to our notes. Okay. And so what I'm going to do is just spend a few minutes talking to you about some of the basic features and characteristics of arteries and veins. Okay. And a few topics may come up like blood pressure and so forth during our conversation. Okay, so anatomy of blood vessels. Okay, and for this conversation, it might be helpful for you to have page 215 open in front of you. Okay, the first is I need to define a term which I think you already know because it's come up in lab actually, and that's the lumen. Okay, right? Blood vessels are going to have a lumen. The lumen is the open hollow space inside the blood vessel. Okay, just like your garden hose has an internal hollow space that the water goes across, your blood vessels have a hollow space that the blood goes across, and that's the lumen. Okay, let's take a look at the arteries. Okay. The arteries, as you can see on page 215, are made of 3 layers of tissue. Okay. The innermost layer is called the endothelium. Let's see, innermost, that's the made of endothelium. And you know that endothelium is simply the term endothelium is a cardiovascular term that refers to epithelium, right? Endothelium is just a specialized version of epithelium. And you know that epithelium covers the surfaces of body structures, both inside and outside the body. Okay, this is specialized epithelium. Okay. The middle layer, okay, this is made of smooth muscle and some elastic fibers, which is to say proteins that have stretchiness to them. So the middlemost is made of smooth muscle and elastic fibers, where the fibers are simply chains of protein. Okay. So, you know, if you did cut an artery in your body, now, I mean, if you cut a major artery, that's very serious, right? I mean, you could die from that. But if you cut an artery, or if it's partially damaged and you're bleeding, you know, the body will try to constrict its smooth muscle tissue to slow the loss of blood. Unfortunately, the body cannot completely control the loss of blood that way, but it can reduce the rate at which you're losing blood loss. It will reduce the rate that you're losing blood. Okay. And then you have the outermost layer, which is made of a variety of connective tissue. Okay. So it's really the elasticity of the middlemost layer of the artery that I want to talk to you about or ask you some questions about. So here's a question. Why is it important that your arteries have elasticity? Why is it important that your arteries have elasticity? There's actually 2 answers that I'm fishing for. Okay, Nick says so they don't break. That's a very practical answer, and I love it. He's absolutely correct, right? Think about it. If you have a hurricane coming up the coastline and there's some trees that are embedded in the soil at the coastline, well, what kind of trees survive? Isn't it those trees that have the ability to bend and flex a little bit versus those that are rigid and they don't bend at all? They tend to just snap and die, right? So the elasticity of the arteries helps to prevent structural damage to the blood vessel. Okay, helps prevent structural damage to the blood vessel by flexing. And then there's another important feature here. Quinn, you say so they can push the blood through. I can see what you're saying. I would ask for a little bit more though. Why is it important that your arteries have elasticity? Okay, we're almost out of time, so let me try to finish this up for us so that we have a clean starting point for next class. Quinn, you say like a pump changing pressure. Okay, so I like that you brought up the topic of pressure, but I don't like that you talk about changing pressure. Alyssa, so they can push blood around a clot if one forms. I think that's also a practically useful idea. Of course, we don't want clots to be unnaturally forming. That could be harmful to us, but okay, I will give you that, Alyssa. The second thing is so that blood pressure can remain constant. Think about it, folks. By having the ability to stretch, the blood pressure gets to stay constant, okay? Let's say you have a blood vessel, okay? Let's say you have a blood vessel where the blood pressure is at a certain amount, okay? Maybe it's 80 millimeters of mercury. All of a sudden, the heart contracts and it tries to squeeze a larger volume of blood into that same space. If the blood vessel doesn't stretch and you cram more blood into that space, then the blood pressure is going to spike. But if the blood pressure can stretch and get wider to accommodate that increase in blood volume, that means you can reduce the blood pressure spike and effectively keep the blood pressure constant. Okay? Think about that one more time. Okay? If the blood vessel does not stretch and the heart tries to squeeze more blood into the blood vessel, doesn't it make sense that the pressure is going to have to go up? Generally, we don't want that to happen. So Mother Nature created blood vessels, the arteries, so that they can stretch. So as more blood comes into them, they can widen to make more space for a larger volume of blood, which allows you to maintain a relatively constant blood pressure. Okay, Emily, you mentioned about good body temperature. I could see us getting there if we're talking about the heat content that's in the blood. Okay, so that's a little bit related, yeah. Okay. Folks, does it make sense how having the ability to stretch ensures that we keep a constant blood pressure? Is that working for you, or do we need to do some drawing? How about the rest of you folks? Are you okay right now? Okay. If necessary, maybe we'll pick this up next time. If you think about this over the next day and you're bothered by it, we can start next class by doing a drawing about this to try to illustrate this principle. Okay? So, let me stop sharing. Okay? Folks, Thursday, you have your second lab exam. Okay? So in last week's email, I did send out some study points about what you should be focusing on. And Thursday, we'll only have the lab exam for the lab period. There will not be a lab activity. So Thursday, we have normal lecture. and then there will be no lab time together because you will have your lab exam to do. Okay? Do you have any questions about the potential lab exam on Thursday? Okay, obviously, I will remind you on Thursday that you got to take your lab exam, okay? So Quinn, after you complete your lab exam on Thursday, there are no more labs and you are done with the lab portion of the course, okay? Anything else? All right then, folks, study hard for your exam. Stay safe, and I will see you on Thursday, okay? Have a good afternoon.